Welcome to Maths with EJD. In this video, I'll be talking about some of positive integers and prime factorization under mathematical induction. This is the second video under mathematical induction. So talking about some of positive integers, right? We have sum of positive integers, And the question under that is straight to the point. Prove by induction, prove by induction that the sum, that the sum of the first n positive integers is n into n plus 1 divided by 2. This is as good as saying that adding from 1 to any number is equal to that number times the number after it divided by 2. So I have previous videos on this under fast math solutions to deal with a case like this. So let's delve into it officially now as we look at mathematical induction. So sum of positive integers, right? Prove by by induction that the sum of the first n possible integers is n equals n plus 1, n into n plus 1 divided by 2, right? So how do we take care of that? First of all, so we have a claim here. So we have a claim, and the claim is that 1 plus 2 plus 3 plus all that up to any particular n is equal to n into n plus 1 divided by 2. That is our claim. Of course, like I told you in the first video, I break this down into 4 steps. But now I can tell you that for each question, right, you can actually follow some well laid out patterns. So one of it will be that, of course, you have a claim. After the claim, you have the base case. You have the base case. The base case is where you say you prove it for maybe maybe n equals 1 and n equals 2. That's your base case. Then the next one will be the inductive hypothesis. Inductive hypothesis. So the inductive hypothesis is where you assume. So assume that the claim is true for n equals k. And finally, you have the inductive step. Inductive step. You have the inductive step. And at the inductive step, that's where you do the real work, where you prove the claim for n equals k plus 1. And finally, then you make your conclusion, right? That once you're able to get it right here, then you can make the conclusion that, okay, conclusion. So the claim is true for all integers or whatever situation you are dealing with, okay? So you have a claim, you do the base case, you do the inductive hypothesis, you do the inductive step, and you have a conclusion. So 1, 2, 3, 4, 5 now. Okay. So let's do this. Now back to what we have. Let me go black. Okay, let me go back to blue, right? So the claim is that the first n positive integers, if you sum them up, you get this thing. Now, one thing about this kind of situation is that now you can see that the left-hand side is like a sum, and the right-hand side is like a formula. So you have to deal with them accordingly. The left-hand side is a sum, the right-hand side is a formula. Okay. And the end goal is that at the end of the day, whatever n is here becomes k plus 1. So you already know the end goal from the beginning. So at the end of the day, for you to, at the inductive step, right, you want to finally get, for every n, you have k plus 1. So this n here is k plus 1. Then this n plus 1 becomes like, first n is k plus 1 plus 1. This is like n plus 1 now, all over 2. So if you're able to get this at the inductive step, then you're good to go. So that is our aim at the end of the day. So we have our claim again. to be 1 plus 2 plus 3 plus n, and 1 plus 2 plus 3 plus everything up to n is equal to n into n plus 1. So let's talk about the base case now. Let's do the base case. So for the base case, right, I'll take 2, n equals 1 and n equals 2. So I say for n equals 1, right-hand side is sum. Right-hand side is a sum, right? You're adding things up. So since n is equal to 1, so you take just 1. So it means the right-hand side, so that tells you that the right-hand side is simply 1 because you're taking just one value. So this 1, that's the right-hand side because it's a sum, okay? So you only have that first one. So on the other hand, you have the left-hand side, which is actually a formula, right? The right-hand side, left-hand side. Oh, sorry. This is left-hand side. Left-hand side is a sum. Left-hand side is a sum. The right-hand side is a formula. Okay, so what's the formula? N into n plus 1. So for n equals 1, so you're just going to say that the right-hand side is equal to 1 into 1 plus 1 all over 2, because n into n plus 1 all over 2. That's 1 into 2 divided by 2. That is simply 2 over 2, and that is 1. So you see the left-hand side is equal to the right-hand side. So for n equals 1, so you see left-hand side is equal to right-hand side is equal to 2. So that means the claim is correct for n equals 1. So for n equals 2, I mean, this is like extra, it's not necessary. Once it is true for n equals 1, you're fine. But I just like to do this just to establish what we are doing. So the left-hand side again would be, now you have again 1 plus 2 plus 3 plus all that plus n equals n into n plus 1 all over 2, right? So the left-hand side, you now have n equals 2. That means you add up the first two numbers. So you have 1 plus 2, and that is equal to 3. Then the right-hand side, which is a formula now, you put 2. N is 2. So you put, for sums, you add them up. For formulas, you impute values. So you have 2 into 2 plus 1 all over 2. That is 2 times 3 over 2. 2 cancels 2, and you have 3. So you see, for the left-hand side, you have 3. The right-hand side, you also have 3. So that means that left-hand side is equal to right-hand side is equal to 3. So you can say, therefore, the claim is true for n equals 1, n equals 2. That's the base case. So the next thing we want to do now is the inductive hypothesis. That's the second step. So inductive hypothesis. Let me go something bright. Let's go this. So we have the inductive hypothesis now. Inductive hypothesis. So, and what do you do here? You just assume the claim is true, for n equals k. So we are assuming, and the best we can do here is to say 1 plus 2 plus 3 plus everything up to n now becomes k, right? So instead of writing n, you have k. And that is equal to k into k plus 1 divided by 2. All right? So that's the best you can do at this inductive hypothesis. You are just assuming. So it's a hypothesis, so it's an assumption. So once that is taken care of, then you go ahead to talk about the inductive step. So now we talk about the inductive step. So what do you do at the inductive step? So here we prove the claim. For n equals k plus 1. And I already told you that for you to know that the claim is true, 1 plus 2 plus 3 plus all that up to n is equal to n into n plus 1 all over 2. So for you to know that the claim is true, it means that you want to be able to show us that this expression for every n, you have k plus 1. So you have k plus 1 into k plus 1 plus 1 all over 2. So for every n, you now have k plus 1. That is when you know that the inductive step is correct. So here we prove the claim for n equals k plus 1. So what do? We have 1 plus 2 plus 3 plus all that plus, at the inductive hypothesis stage, we already have n changing to k, and this is k into k plus 1 all over 2. Okay? Now that we have this, you already know the end goal, and that makes it very interesting. So you have k into k plus 1 over 2, and you want to end up here. And to do that, let's see. So since this is k, right, the next step after k is k plus 1. So we can say that for n equals k plus 1 now. So it means you have 1 plus 2 plus 3 plus all that plus k, which we know is also equal to k into k plus 1 all over 2. So uh, you see that these two are equal at this point, right? See that these two are equal, k into k plus 1 all over 2. So you see that this expression is equal to this expression. But if at k plus 1, now k plus 1 is a step after k. So it means if you add k plus 1 to this side, the only way to balance the other side is to also add k plus 1 to that. So as you add k plus 1 here, you also add k plus 1 here. That's the only way to ensure there's a balance. All right. So I guess I also want to go coloring here. Let's do okay, let me go this. Okay, so at this stage now, you already know where you're going to. So we can write this out neatly. We have 1 plus 2 plus 3 plus all this plus k plus 1 equals k into k plus 1 all over 2 plus k plus 1 all over 1. So now you see, so now that this is settled, then you have to focus on this side until you get the result you want, which means that for every k, you now have k plus 1. So that at the end of the day, we are expecting to have k plus 1 into k plus 1 plus 1 all over 2, like that. So now we have LCM of this is 2. So 2 into is 1. 1 times k, you have k into k plus 1 plus 1 in 2 is 2. You have 2 into k plus 1. So, and then we simplify this until we get what we want. So here, k plus 1 is common. So you have k plus 1 into k plus 2 all over 2. Now, things are looking good already because this k plus 1 here, we already have it out here. Then we now need k plus 1, and we have k plus 2. That looks like we can actually achieve it. So we have k plus 1 into k plus 1 because k plus 2 is k plus 1 plus 1. This is all over 2. And then that means we can actually go ahead and have k plus 1 into k plus 1 plus 1 all divided by 2. Okay, so now we have achieved our result. So we can go to the conclusion. We can do the conclusion. And what does the conclusion tell us? So that's the fifth stage. So first of all, you have the claim, n equals, you have the claim, right? Then you do the base step. Then you do the inductive hypothesis. Then you do the inductive step, which we have just completed here. And we have found it to be true based on what we are expecting. And then you have to make a conclusion. You can now say, since 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 the claim is true for n equals 1. Okay, well, or we can even summarize that. So you can say, since the claim is true for both the base step, for both the base step and inductive step, or you can say base and inductive steps, an inductive step, then it is true for all natural numbers, all right? It is true for all natural numbers. So that puts paid to that first question, all right? That's puts paid to the first question. Okay, so let's go ahead to talk about, this in this lesson, right? In this video, our focus is on sum of positive integers and prime factorization. So we have a question related to prime factorization. So prime factorization is the next question. Prime factorization. Very simple thing. but then it requires logic, just like you already know. Mathematical induction is all about logic. It's all about writing proofs. So see the second question says to use, I've told you I'm going to just be using strong induction. Strong induction is about proving the base case, assuming for K and proving K plus one. But weak induction is you just assume K and then prove K plus one. So I'm going to be using strong induction all the way. So this question says to use strong induction, use strong induction to prove that every to prove that every positive integer to prove that every positive integer, that's natural number, right? To prove that every positive integer greater than one can be expressed can be expressed as a product of prime numbers, as a product of prime numbers, as a product of prime numbers. Now, in this case, this is not going to involve any formula as such like we had initially, right? It's not necessarily not going to involve any formula like we had initially. So, but then all these steps are still necessary. We are going to, so here you can break it down. What is the claim? The claim is that every positive integer, every positive integer, greater greater than one can be expressed, can be expressed as a product, as a product of prime numbers, as a product of prime numbers. That is our base claim, as a product of prime numbers. So that's more like to say every positive integer, right? So we are saying that every z plus, we use z for positive integer. So every z plus, that is greater than 1 is such that z plus can be written as a product of prime numbers. So you have, so let's say the prime numbers are P1 and P2. So you can always write every positive integer greater than 1 as a product of prime numbers. So prime number 1 and prime number 2. So that's how we can break that down. That's the claim, okay? So the next thing is want to do the base case. So, for me, I like to use, for base case, I like to do, instead of just doing n equals 1, I do n equals 2. But in this case, we may have a bit of twist because we are saying that it is every positive integer greater than 1. So for the base case now, so you have the first no the first prime number, right? The first number, positive integer after one. First, how do I express this? Let me just call it z. Let me call it z plus 1, which is 2, right? That's the first positive integer greater than 1. So z1 plus is 2. And of course, that's simply 2. 2 is already a prime number, so there's nothing you can do to that. So that is something that, like our, n equals 1, because we are talking about integers greater than 1. So we can also talk about z2 plus. So the next positive integer greater than 1, apart from 2, will be 3 again, you know. So that's 3. Again, 3 is a positive, is a prime number on its own already, so we don't have to worry. Well, I can even stretch it, right? So that to drive the point home. So we can have z3 plus, and that is 4. 4 is the next positive integer after 3. And that is actually 2 multiplied by 2. And this is like your P1 and P2. So 2 and 2 are prime numbers. And that's the kind of idea, right? In fact, let me keep stretching it. This is not necessary, right? But I'm just going all the way. So Z4 plus would be 5, right? And 5 is simply a prime number. So that's all we have. And then let me even go further and talk about Z5 plus. So positive integer greater than 1. So the next one is 6, and it's simply 2 multiplied by 3. So 2 multiplied by 3. So 2 is like your P1, and 3 is like your P2. That's like your positive, your prime numbers, right? So you see now, there are two scenarios here. There are two cases, and this is going to help us, in doing other things we'll have to do. So there are two cases here. The first case is you have those cases where the numbers are straight prime numbers first. All right. And then you have cases where you have cases where you now have the numbers themselves being expressed as the product of two prime numbers. Okay, so those are the cases we have seen. So you can see the base case here is really stretched out, but it's okay. I mean, for understanding, I think that's not a bad idea at all. Okay, so let's go back and then, so that's the base case. So let's do the inductive step. Step. So not inductive step yet. It's inductive hypothesis. That's the third stage. So you have a claim, you have the base case, you have the inductive hypothesis, you have the inductive step, and finally you have the inductive, yeah, and then finally you have the conclusion. So for the inductive hypothesis now, assume 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 the claim is true. Assume the claim is true. The claim is that all positive integers greater than 1 can be expressed as the product of two prime numbers, right? So here we are assuming that that claim is true for n equals k, for n equals k. So what does that mean? So it simply means that if we have a particular, since I've been numbering it like that, so if we have a z plus k, and that is simply going to be p1 multiplied by p2. So prime number 1 and prime number 2. So that's that, right? So finally, we can talk about the inductive step, which is the final step. Like that's like the last fight, you know. So step, inductive step. So for the inductive step now, we have to prove the claim. We have to prove the claim. We have to prove the claim for n equals k plus 1. So how do we do that? So here we are not dealing with formulas, so that's the issue. So and just like you've seen already in the base case, we have two cases, right? We have cases where the numbers are already prime numbers, like 2, 3, and 5, and we have cases where the where the numbers are already prime numbers, and we have cases where the numbers they are products of prime numbers. Those are cases we have. So at the inductive steps, we have to consider those two cases. So case one, right? Case one. Of course, those are cases where k plus 1 is already a prime number. Okay? K plus 1 is already a prime number. Or, I mean, based on my notation, right? Since I'm using Z1, Z2, so let me just say Z plus. So Z plus K plus 1 is already a prime number. So in that case, it's done, right? You don't have to worry about that. So in this case, K plus 1 is 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 just is already expressed. I mean, allow me to use already twice. Is already expressed. Is already expressed or expressed as a product of prime numbers, which is simply itself. All right. So that is just itself. So that's the simpler case where the number is already a prime number. So that's itself, right? That's case one. So for case two now, so in the case of case two, right? K plus 1. Okay. Don't forget, I keep using my notation, and I keep forgetting. So Z plus. So case 2 now, Z plus K plus 1 is composite. It's composite. That is it. That means that it is not prime. That means it is not prime. So in this case now, what do we do? in this case, z plus k plus 1 can be factored, can be factored, can be factored into two positive integers, into two positive integers, into two positive integers, p1 and p2, such that you know, uh 2 is less than or equal to p1. So that means the first integer can be less than or equal to 2, or better still, let's do it this way. So integers p1 and p2 such that 2 is less than or equal to p1 comma p2, which is less than or equal to k. That means that whatever the last k we have is, so the two prime numbers are between 2 and k. So the first one can be just like the cases you've seen, like 4 and 6. 4 is 2 times 2, right? So p1 can actually be 2. In the case of 4 now, for 4, you have p1, p2 is 2 times 2. That means both p1 and p2 are 2 each. But then, so p1 can be 2, or p2 can be anything less than k, or k itself, right? So in the case of 5, in the case of 6, right, you have p1, p2, which is 2 times 3, 6. So this is p1 and this is p2, just like this is p1 and this is p2. So if that is the case now, it means that we can express, so uh we can now say that since p1 and p2 are both less than k plus 1, are both less than k plus 1, by the inductive hypothesis, hypothesis, by the inductive hypothesis, both P1 and P2, right, can be expressed as a product of prime numbers, as a product of prime numbers, as a product of prime numbers. All right. So basically, we are saying that z plus k plus 1 is actually possible to be p1 multiplied by p2, uh, you know, and we know that the condition for this is that 2 is less than or equal to p1, p2 is less than or equal to k. All right. So with this, we have, of course, you see, this is not a formula, some kind of thing. So you have to just use reasoning. And, that now finally leads us to the conclusion, right? So we finally go to the conclusion. So what do we conclude here? So in the conclusion, we say, by the principle of strong induction, by the principle of strong induction, what do we say? Every positive integer, or you can say the claim is true, right? If you like, but here we are stating the claim. So every positive integer, greater than 1, than 1, greater than 1, can be expressed, as a product of prime numbers. And that is it. So that is done. So again, if you have not signed up to this page, to this channel, you want to be sure to do that. Subscribe, hit the notification bell so you can get notified whenever a new video is released. Then the next thing you want to do is you want to make comments about, if you need solution to a problem, if you want us to treat a topic, then of course you want to share to people that will need it, because I know this is very useful for so many people. So please keep coming back. I appreciate you all the time. See you in the next video.